So, good morning once more. Today we will start continuous time Fourier transform. Well, remember in the previous chapter we have seen that continuous time periodic signals can be, expressed as linear combinations of harmonics. So, in other words, complex exponentials. And so how we develop the Fourier series expansion, Fourier series representation. Well, this representation is actually effective in order to find the outputs for LTI systems, because complex exponentials are eigenfunctions for the LTI systems. So you can find input-output relationship easily. Now today in this chapter we will extend this discussion and see that if we have a signal, continuous time signals, which is not periodic, can be represented as this complex exponentials. So first, we will start with some intuitions, with some motivations. Assume that I have a signal x of t, and it is given as this. It is a periodic waveform, and in a single period, assume that it's defined as this. So in between, if t is in between minus t1 and t1, it is 1, and it is otherwise within a period. So t0 is the period. So within a period, I have this, let's say, pulse, rectangular pulse here. Well, if you go and remember the Fourier series coefficients of AK, we have calculated them as this for the signal in the previous chapter. Well, now now consider the continuous envelope. So I have those AKs here, I have those AKs, and there is this continuous envelope that is going at the tips of those AK coefficients. Well, I can define this envelope as a continuous signal, and by assuming that omega is k times omega 0, I can define this omega 0. I can define this envelope as 2 times sine omega t1 over omega, and it is independent of the period in this case. So I have this envelope defined over the tips of the AK coefficients, and this envelope does not depend on the period t0. Well, as I increase t0, in other words, as I decrease omega 0, so increasing t0 means that I decrease omega 0, this envelope is denser. What does it mean? So I'm taking the samples right here. I'm taking the samples here at omega equals k omega 0. So these are my samples here that are taken over this envelope. As I increase omega 0, now I am having denser samples. So as t0 goes to infinity, so it means that this t0 is going to infinity over there. So if this is the case, then this periodic square waveform becomes a single pulse. So these are going to infinity, these are going to infinity. So I only have a rectangular pulse left at, let's say, at the initial period. So in other words, my periodic waveform is now a single waveform. So it is just a single pulse. The Fourier series coefficients AK become infinitely close samples of the envelope. So I'm having denser samples of this envelope. And in the limit, I have now a continuous waveform here over there. So the AK coefficients are having infinite small, let's say, interval in between. So it means that now the envelope is now a continuous signal. So I have, as this t0 goes to infinity, I have the periodic waveform becoming the aperiodic single pulse here, and the coefficients, Fourier series expansion coefficients, now becoming a continuous waveform. So actually this is the motivation behind the Fourier transform. So we have started with the envelope of the Fourier series coefficients, and as the period goes to infinity, I have a single pulse, so the periodic signal and the signal which is a mere pulse are equal, and the Fourier series coefficients now having a continuous envelope. So the Fourier series coefficients are, in other words, transferred to the let's say Fourier transform. Well, what about the formal definition? Well, first assume that I have a periodic signal x of t, and I have its periodic version, which is x tilde t, and they are illustrated here. So this is my x of t, which is not periodic, and I have x tilde t, which is the periodic version. So I will start with writing the Fourier series analysis and synthesis equations for x tilde t, which is the periodic version. Remember, I have x tilde t can be expressed as summation over k, ak, e to the power j, k, omega 0 t. And of course, I have ak as 1 over t0 integral of x tilde t, e to the power minus j, k, omega 0 t, dt. So these are my, remember, well-known synthesis and analysis equations. So I know that ak is nothing but 1 over t0. So since this integration is over a single period, I know that in the first period, let's say x tilde t is equal to x of t. So I can simply write integral from minus infinity to plus infinity x of t, e to the power minus j, k, omega 0 t, dt. So those limits are now from minus infinity to plus infinity, because this x of t is limited. So let's say this is t0 over 2 minus, and this is t0 over 2. So if this is the case, I have actually, since I will integrate the periodic signal over a period, this turns out that I will integrate the aperiodic version from minus infinity to plus infinity. So in other words, t0 times ak is nothing but x of omega evaluated at omega equals k omega 0, and of course where x of omega is simply defined as integral from minus infinity to plus infinity x of t e to the power minus j omega t dt. So if I define my x of omega as integral x of t to the power minus j omega t dt, then this turns out that t0 ak is nothing but the sampled version of the x of omega, and the samples are at omega equals k omega 0. So if you substitute ak's back, now you have that x tilde t is equal to summation k 1 over t0 x of k omega 0 e to the power j k omega 0 t, and I have t0 as 2 pi over omega 0. So what's the case? Here I have the well-known synthesis equation, and in the synthesis equation I have put this let's say ak that I have already derived here. So I have this x tilde t, and if I continue writing, x tilde t is equal to 1 over 2 pi summation k from minus infinity to plus infinity omega 0 x of k omega 0 e to the power j k omega 0 t. Well, as omega 0 goes to 0, in other words, t0 goes to infinity, I have x tilde t is equal to x of t, just as the previous discussion. So these parts are going to infinity. So I have x tilde t is only left with this single shape here, which is x of t. And I can write this as x of t is equal to 1 over 2 pi integral from minus infinity to plus infinity x of omega e to the power j omega t d omega. So This is the actual formal proof for the Fourier series representation, and this brings us to the Fourier transform or Fourier integral, which is simply x of t is equal to 1 over 2 pi integral from minus infinity to plus infinity x of omega e to the power j omega t d omega. So I have also the actual, let's say, transform from x of t to x of omega. By the way, this was the inverse Fourier transform. So you have x of omega in Fourier representation or in frequency representation. So this is x of t. And this is the forward formula. So you have once x of t, you can find x of omega using the Fourier transform. So x of omega, which is the Fourier transform, is equal to integral from minus infinity to plus infinity x of t e to the power minus j omega t dt. So this is the case. Once you have x of omega, you can find x of t by using the inverse transform. Well, x of omega is called as the Fourier transform of x of t, or it can be referred as the spectrum of x of t. These are also the synthesis and analysis equations for Fourier transform. And if you compare Fourier series and Fourier transform, so these are the, let's say, similarities and the differences. Both represent signals as a linear combination of complex exponentials. So this is the case. Remember, Fourier series is dealing with periodic signals, and it is simply summing the exponential terms. The Fourier transform is, on the other hand, can represent a periodic signals as well, and it is based on the integration of the complex exponentials. Fourier series, actually complex exponentials occur at a discrete set of harmonic related frequencies. So you have k omega 0 and their amplitude. So you have a discrete representation in Fourier series. In Fourier transform, complex exponentials occur at a continuum of frequencies. So you have a continuous representation in frequency domain and have amplitudes x omega over 2 pi. Well, from the development of Fourier transform, the Fourier series coefficients ak of x tilde t are nothing but equally spaced samples of the Fourier transform of xt. So xt is the aperiodic version. Remember, xt is the aperiodic version. X tilde t is the periodic version. So if you have the Fourier transform of xt, you can find the Fourier series expansion coefficients ak for x tilde t by simply sampling x of omega. So this is our case. So Fourier series representation, AK's Fourier series coefficients, AK's and Fourier transform x omega are actually closely related. Well, what about the convergence? Well, similar to the Fourier series representation, Fourier transform representation of a signal x of t exists and equals to this if you have those conditions satisfied. Well, first, if x of t has finite energy, it means that it is square integrable and it is a finite value, then the Fourier transform exists. Or you have Dirichlet's conditions. So what are they? So either this one or those must be satisfied. So if this is the case, then you are done. But if not, or you should check those three conditions. X of t is, what are they? X of t is absolutely integrable as before. X of t has finite number of maxima and minima within any interval. And x of t has a finite number of discontinuities within an interval, and each of these discontinuities are finite. So actually these are as before, so as we have seen in Fourier series representation. Although these conditions are sufficient to guarantee that a signal has Fourier transform, we will see that for periodic signals, these conditions are not satisfied. But actually we will see that if impulses are allowed in the representation, periodic signals can also have Fourier series representation, Fourier transform representation that we will see in a moment. Well, let's start with a single example. X of t is e to the power minus 80 ut, and a is larger than 0. So first check whether condition 1 is satisfied. So it is simply integral minus infinity to plus infinity. So let's say this is 1, this is 2, this is 3. So x of t dt, and this is equal to, of course, e to the power minus at dt. This is 1 over a, and this is, of course, a finite number. So the first condition is satisfied. What about 2 and 3? Let's write here 2 and 3 are satisfied as well. Signal has 1 maxima and 1 discontinuity. So, by the way, let me plot x of t. So it starts from this axis here, vertical axis, and it decays as t is increasing. So it's trivial that it has 1 maxima and 1 discontinuity. Both are occurring at t equals 0, and it has it is absolutely integrable as given here. So I can find the Fourier transform for this signal. So what is this? Let's write the analysis equation. X of t e to the power minus j omega t dt, and it is integral from minus infinity to plus infinity, or I can switch this to 0 because the signal starts from 0. E to the power minus a plus j omega t dt. And if you go and calculate, it is minus 1 over a plus j omega e to the power minus a plus j omega t from 0 to infinity, and it is 1 over a plus j omega. So e to the power minus 80 ut has Fourier transform 1 over a plus j omega. So let's consider this complex number here. What is this? This is, let's say, the real axis, this is the imaginary axis, and this is my complex number a and omega. So what's the norm? The norm is, of course, square root of h squared plus omega squared. So what's the angle? So this is the norm of this a plus j omega, and the angle is tangent inverse omega over a. So what is this complex number here then? 1 over a plus j omega is simply, let's write here, it is equal to 1 over square root of a squared plus omega squared e to the power minus tangent inverse omega over a. So there's a minus here because this is in the denominator. So the angle is reversed from going down to up. So this 1 over a plus j omega is equal to 1 over square root of a squared plus omega squared e to the power minus, so this is the angle, e to the power minus tangent inverse omega over a is the, let's say, complex number in polar form. So if you want to plot it, it is simply, let's start with the magnitude. So it is decaying. It is 1 over a at the maximum. What about the angle? So let's plot angle of x of omega. Well, it is somehow tricky to plot, but so it is, remember, tangent inverse omega over a. So it's a, I have the angle minus pi over 4 at minus a. I have the angle pi over 4. So it is, let's say, this and this. And when omega is increasing, it is approaching minus pi over 2. Let's do this. And also it is approaching pi over 2 for increasing omega. So in the limit, it is going to pi over 2 and minus pi over 2. And for omega equals a, the angle is minus pi over 4. And for omega equals minus a, the angle is pi over 4. Well, you can see it as well. Remember, what was it? It was a plus j omega. If omega is equal to a, so you have a plus ja. It is 45 degrees or pi over 5, pi over 4. So it is in denominator. So you have minus here. For omega equals minus a, so you have 1 over a plus j omega. So this is minus 45 degrees. So since it is in denominator, you have 45 degrees or pi over 4 radians for omega equals minus a. So as omega going to infinity, what is it? As omega going to infinity, you have a pure complex number, and the angle is pi over 2, and it is, of course, minus pi over 2 for 1 over a plus j omega. So simply you can observe that those, let's say, angles are valid. So now I have another example, which is x of t is equal e to the power minus a absolute t. So it is, let's try to plot it. So this is t, x of t. So what about x of omega? So x of omega is, again, I will start with the free integral e to the power minus j omega t dt. This is equal to integral from minus infinity to 0 e to the power at e to the power minus j omega t dt. Well, of course, when you check this for t negative, for t negative, this is minus t, right? The absolute sign. When I get rid of the absolute sign, I have minus t. So e to the power minus a times minus t. So I have e to the power at here. Plus integral from 0 to infinity. So if t is positive, then I will directly write this as e to the power minus at. It is e to the power minus at, e to the power minus j omega t dt. Well, if you evaluate the integral, it is 1 over a minus j omega e to the power a minus j omega t from minus infinity to 0 plus minus 1 over a plus j omega e to the power minus a plus j omega t from 0 to infinity. So if you evaluate this, I'll directly write that it is 2a over a squared plus omega squared. So it is a real number. So it means that angle of x of omega is 0, and the norm is simply 2a over a squared plus omega squared. So if you plot x of omega, it is nothing but this signal. And 2 over a is the maximum. So if you put here omega equals 0, then this will cancel. So you have 2 over a as the peak value. And as omega goes to infinity, of course, as this goes to infinity, the whole is going to 0. So this is why in the limit I have, let's say, x of omega going to 0. So now the next example is the impulse. X of t is equal to delta t. So what is x of omega? If you write it as integral from minus infinity plus infinity, impulse of t e to the power minus j omega t dt. By shifting property, it is simply e to the power minus j omega 0. Remember, this impulse is non-zero when t equals 0. So simply put here 0. So this is 1. So the Fourier transform of delta t is simply 1. If you plot this, it is simply this. So a constant value. Well, these are just simple, calculus, basic calculus. It is easy to evaluate. Next, we have the important, let's say, signals, which is the rect t and sinc t. So rect t is nothing but 1 for absolute t is smaller than 1 over 2, and it is 0 elsewhere. So let me try to write this in this form. So what is this? It is minus 1 over 2 smaller than t smaller than 1 over 2. So if you plot this rect t, it is simply this. So it is 1. So in between minus 1 over 10, 1 over 2, my rect t signal is nothing but 1. And it is 0 otherwise. So this was the, let's say, easy version. What about sinc? So sinc is defined as sine pi t over pi t. First, note that what about this sinc t at integer values? So if t equals, let me write here, if t equals, let's say 1, what is it? Sine pi over pi. You know that sine pi is 0, so this is simply 0 for t equals 1. What about t equals 2? At t equals 2, you have sine 2 pi over 2 pi. Again, sine 2 pi is 0, so this is again 0. So at integer values, so plus minus 1, plus minus 2, plus minus 3, this sinc is all, let's say, 0. So let me plot it here. Well, let me plot this as the so let me draw this here. So this is your sinc t. So I have shown that at plus 1, at plus 2, at plus 3, at minus 1, at minus 2, at minus 3, the signal is all 0. So it will pass through those points. So what about t equals 0? At t equals 0, I have sine 0 over 0. Well, sine 0 over 0 is should let's say remind you the L'Hopital's rule. So it's remember solves such ambiguity 0 over 0, infinity over infinity. So it tells you that take the derivative of the numerator, take the derivative of the denominator, and evaluate limit once more. So sine pi t has the Fourier transform of pi times cosine. So what is this? If you derivate sine, so if you apply L'Hopital's rule, you have pi cosine pi t over pi. So those cancel out. So at t equals 0, I have cosine 0, which is equal to 1. So a sinc signal has maximum value of 1 at 0, and it is 0 at other integer values. So what about the rest? So you know that if you apply this sandwich theorem to evaluate the integral, sine is nothing but a number between plus minus 1. So pi t, on the other hand, is increasing which t is going to infinity, or it is increasing in the absolute value if t is going to plus infinity. So this value is decreasing in absolute sense as t is going to plus minus infinity. So this is how Ceng looks like. So the peak values are decreasing as t is going to plus minus infinity. So this is the shape of your Ceng signal. Well, these rect t and Ceng t are important. So actually we'll clarify this with an example. So let's start with the rectangular pulse. What does it tell you? It is 1 for t, absolute t smaller than t1, and it is 0 elsewhere. So let me write it here. What does it tell you? Minus t1 smaller than t1. So if this is the case, the rectangular pulse is 1. So if you check with this rect t signal, if you check with this, it is clear that x of t is nothing but rect t over 2t1. So if you put here t over 2t1, so minus 1 over 2 smaller than t over 2t1 smaller than 1 over 2. So what does it tell you? Minus 2t1 over 2 smaller than t smaller than 2t1 over 2. So t is if t is larger than minus t1 and smaller than t1, you have 1. So we have verified that this x of t is nothing but, so those cancel out, and I have this representation initially. So we have seen that this rectangular pulse rectangular pulse x of t is nothing but rect t over 2t1. So let's write the Fourier transform. X of omega is integral from minus infinity to plus infinity x of t e to power minus j omega t dt, and this is integral from minus t1 to t1 e to power minus j omega t dt, and it's equal to minus 1 over j omega e to power minus j omega t from minus t1 to t1. So if you evaluate, let's write minus 1 over j omega e to power minus j omega t1 minus e to power j omega t1, and it is equal to 2 over omega e to the power j omega t1 minus e to the power minus j omega t1 over 2j. So what does this remind you? E to the power something minus e to the power minus something over 2j. So this is simply 2 over omega sine omega t1. Well, what does it tell you? If you have x of t, rect t over 2t1, x omega is 2 over omega sine omega t1. Well, we will actually make this resemble look better. So it is, let me do some trick, 2t1 times sine omega t1 over omega t1. It is 2t1 sine omega t1 over pi times pi over omega t1 over pi. Well, sine something pi over something pi. Of course, this is Ceng something. So it is 2t1 Ceng omega t1 over pi. So remember, what was your Ceng? Your Ceng was sine pi t over pi t. So if I replace this t with another variable, then this is sinc of this variable. So I have sine, instead of t now I have omega t1 over pi over omega t1 over pi times pi. So this is simply sinc omega t1 over pi. So this is my signal. So if I want to plot this, so what is this? Well, first note that if the inside of sinc is integer, then I have 0. So for this to be integer, omega must be, let's say, the order of pi over t1. So if omega is pi over t1, 2 pi over t1, 3 pi over t1, or their minuses, then the sinc is 0. What about the peak value? I know that this has peak value of 1. Sinc has peak value of 1. So I can easily plot it as this. This is at the peak, it is 2t1. And if omega is pi over t1, it is 0. If it is 2 pi over t1, it is again 0. And the same holds for the negatives, minus pi over t1, minus 2 pi over t1, and it goes on to infinity. So this is how does this signal looks like. Of course, the peak value is decreasing gradually. So this peak is decreasing as you go to plus minus infinity. So it is easy to plot actually once you know the shape of this basic sinc. So what do we have? We have seen that rect t over 2t1 has the Fourier transform of 2t1 times sinc omega t1 over pi. So rect t over 2 t1 has the Fourier transform 2t1 sinc omega t1 over pi. So what about rect t? Then rect t has Fourier transform of sinc omega over 2 pi, or in other words, sinc f, if of course f is equal to omega over 2 pi. So rect t has Fourier transform of sinc f. Well, these are basic scaling properties, and we will see them in the next lecture. But once note that rect t over 2t1 has Fourier transform of 2t1 sinc omega t1 over pi, and rect t has Fourier transform of sinc f, and f is omega over 2 pi. Well, what if I have just the opposite? So if I have x of omega, then what is the corresponding x of t? So let's write it here. X of omega is nothing but rect omega over 2 omega. By the way, if you are mixed with omegas and capital omegas, so this omega is variable, okay? Of course, it is variable, so it is here or it is here. So omega is the variable in Fourier domain or in frequency domain, and t is the variable in time domain. Well, in this example, this omega is of course a constant number, and the smaller case omega is my variable in frequency domain. So x of omega is rect omega over 2 omega. So if you want to find x of t, so x of t is nothing but 1 over 2 pi integral from minus infinity to plus infinity x of omega e to the power j omega t d omega. So this is my synthesis equation. So it is equal to 1 over 2 pi integral from minus omega to plus omega e to the power j omega t d omega. and it is 1 over 2 pi 1 over jt e to the power j omega t from minus omega to plus omega. By the way, well, note that I'm trying to find x of t. Of course, the result of this integration should not depend on omega. So here omega is the integration variable. So if I evaluate the integral, the result should only depend on t. And of course, it is the same here. So when I try to find the Fourier transform, the integration is with respect to t time. So in the result, I should not have any t variable. So I should only have omega as the independent variable. So if you continue, this is equal to, let me write here, this is equal to omega, so omega over pi. So I will skip some terms, but you can evaluate them by yourself. Sine omega t over pi times pi over omega t over pi times pi. So this omega is, of course, they are all the capital omegas because I'm in time domain. So I have t here, I have t here. Since I'm in time domain, I should not have smaller omegas. So this is nothing but omega, capital omega, of course, over pi times sinc omega t over pi. So omega over pi times sinc omega t over pi. So if you plot this, again, this is the peak value. Of course, this is the peak value. Let me directly plot this. This is t, this is the peak value, which is omega over pi. Well, what I know that if the inner side is integer, sinc is 0. For this inner side to be integer, t must be multiple of pi over omega. So if this is pi over omega, this is 0. If this is 2 pi over omega, this is 0. If this is again minus pi over omega, and this is minus 2 pi over omega. So this is the Fourier transform of this basic rectangular, this is the inverse Fourier transform of this basic rectangular pulse. So I have again some notes. Rect t has Fourier transform of sinc omega over 2 pi, and sinc t has Fourier transform of rect omega over 2 pi. So this is my observation. A rect t in time domain corresponds to a sinc in frequency domain and vice versa. So if you have a rectangular signal in time domain, in frequency domain you have sinc, or if you have, let's say, sinc in time domain, you have rect in frequency domain. So this is the duality property that we will see in a moment. As rect t has a shorter duration, sinc has a longer, and vice versa. So what does it tell you? If you, in this case, if you, let's say, increase omega, what's happening if we increase omega? So let's plot x of omega. So this is plus omega, this is minus omega. So if you increase omega, it means that this signal is extending. But if you increase omega here, this signal is, the main lobe is, becoming, let's say, narrower or shorter. Or if you decrease this omega here, it means that omega, this signal is, becoming shorter. If omega is decreasing here, it means that pi over omega is increasing. So the main lobe is increasing in length. So this is the case. So here I have, let me stop here. We will next continue with the response of LTI systems to complex exponentials. So this was the, one of the basic motivations that we represent signals as complex exponentials. If you have an LTI system and if you have a complex exponential, remember this e to the power st is the eigenfunction of your LTI system, so you can find input-output relationship easily. So let's stop here and let me stop the recording.